We have done most of the work. So finding the shortest path is going to be super easy. First, I'm going to rename this method to getShortestPath. Always pay great attention to the name of your method and the return type. So here we're asking for the shortest path, but we're returning an integer. This is a common problem that I see in a lot of people's code, even developers with years of experience. It's like asking for a book, but getting an airplane. Don't write code like this. So what should we return here? We want to return a path object. This path should specify a series of steps, okay? So let's add a new class here, path. We give it a list of strings, list of string. In this program, we're storing string objects in our graph, but in a real application, we want to store person objects or cities or airports. So if we store person objects in our graph, the path class should store a list of persons, not node objects, because node is an implementation detail of our graph class. We don't want to expose it outside of the graph, okay? So let's import the list class. We call this field nodes and set it to a new array list. Now, because this is private, we cannot access it from the outside. So here we need a public method for adding a new node. So string node. And here we call nodes.add node. Simple as that. If this concept is foreign to you, you need to watch the second part of my Ultimate Java series. This is all about object-oriented programming. All right, back to our graph class. So here we want to return a path object. That is better. Now, in this method, we should create a hash table for storing the previous nodes. So we need a map of node to node. We call it previous nodes and set it to a new hash map. Now here, we're not going to initialize this like how we did with the distances table. Instead, when we discover a new distance or a shorter path, we're going to update our previous nodes table. So previous nodes dot put, the target is edge.to, that is our neighbor, and the previous node is where we are right now, the current node, okay? Now, once we're done here, at the end, we can build the shortest path using a stack. So let's say we want to find the shortest path between A and E. We know that we arrived at E via B, and we arrived at B via A. So here we can add all these previous nodes to a stack, and then pop the stack, and then these nodes are going to come out in the right order. But initially, we want to add the target node because this is not in the previous nodes column, okay? So after our while loop, let's create a stack. We're going to use the implementation in the java.util package. So in this stack, we're going to have a bunch of nodes. Initially, we want to add the ending node to the stack. So stack.push nodes.get to. Now we want to find all the previous nodes. So we declare a variable like previous. And here we go to our previous nodes hash table and get the previous of this target node. Now I don't want to repeat this expression over here. So let's extract this and store it in a separate variable on the top. Later, we're going to add validation. So that would be another use case for this refactoring. ToNode equals nodes.get to. Now, let's fix this error. So we pass ToNode and ToNode. All right. Now, while this previous is not null, we're going to push this previous node onto our stack. So stack.push previous, and then set previous to the previous of the current node. So we go to our hash table one more time and get the previous node of this node. Our stack is ready. Now we can create a path object from this stack. So let's create a path object. While the stack is not empty, we're going to call path.add. Here we pop the stack. This will return a node object, but we need a string. So we access the label field. And finally, we'll return the path object. Now our code is getting too lengthy. So I would prefer to extract all this logic into a separate private method. Let's call that private path build path. Here we need the target node, to node. Now we can move all this logic over here. Cut, and then paste it here. We also need the previous nodes, so let's add that as a parameter. Map of node to node called previous nodes. So this method needs two parameters, a hash table and a target node. Now back to our find shortest path method. Here we can call this method, give it the previous nodes and the target node. That is better. Now we have one compilation error here. Let's see what is that. I forgot to return the path for our new method. Now let's test this implementation. So here in the main class, I've created a very simple graph. We only have 3 nodes. We have an edge from A to B with a weight of 1, one from B to C with a weight of 2, and a direct edge from A to C with the weight of 10. Obviously, the shortest path from A to C is via B, even though we have a direct path from A to C. But let's verify this. So let's call graph that gets shortest path from A to C, store the result over here, and then print it on the console. So this is the default representation of an object as a string. To fix this, we have to overwrite the toString method in the path class. So over here, that is super easy. We have done this several times before. We generate a toString method. And here, we simply call nodes.toString. Now let's test this one more time. There you go. So here's the shortest path from A to C. Now, what if we pass an invalid node here, like K? We get a null pointer exception. So we need to go back to our graph class and perform validation. After we get the from node, we want to make sure it's not null. If it's null, we're going to throw a new illegal argument exception. Similarly, for the to node, we're going to check to see if it's null. If it is, we're going to throw a new illegal argument exception. So this is the complete implementation of Dijkstra's shortest path algorithm.